What if everything we think we know about the universe is just the surface of something far stranger? Picture this: every star you've ever seen, every galaxy swirling in the night sky, is merely the visible fraction of a reality teeming with secrets we're only beginning to grasp. Beyond the cosmic veil, there are forces at work so bizarre, so utterly beyond human intuition, that even our most brilliant minds struggle to explain them. This isn't just about distant stars or cold, empty space. This is about the fabric of existence itself, dark matter weaving through the cosmos like invisible threads, black holes bending time and space into knots, and phenomena so mysterious they make the wildest science fiction seem tame. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. That feeling is just the beginning. Hidden in the darkness between the stars are puzzles that could rewrite the laws of physics, cosmic whispers of energy we can't detect, structures so vast they shouldn't exist, and perhaps even doorways to dimensions beyond our own. Scientists call these the universe's most enigmatic regions, and for good reason. They defy logic, challenge our tools, and force us to question what's truly possible. But here's the thrilling part: we're on the brink of breakthroughs that could shatter our understanding of reality itself. This journey isn't just for astrophysicists or starry-eyed dreamers. It's for anyone who's ever wondered what lies beyond the limits of human knowledge. Over the next few minutes, we'll venture into the unexplored corners of the cosmos, where dark matter clumps into invisible mountains, where quasars blast energy like cosmic lighthouses, and where the very laws of nature might unravel. We'll examine the theories that could explain these mysteries, from wormholes to multiverses, and meet the daring scientists racing to solve them. So buckle up. By the time we're done, you won't just see the night sky differently. You'll feel it like a secret waiting to be uncovered, a story begging to be told. The universe is far stranger than we've been taught, and it's time to pull back the veil. The cosmic veil isn't some physical curtain hanging in space. It's the tantalizing line where our understanding of the universe hits a wall. Imagine standing at the edge of an endless ocean, watching waves crash just beyond the reach of your flashlight. That's how scientists feel when they study phenomena like black holes, where gravity grows so strong that not even light can escape. Or dark energy, that mysterious force stretching the cosmos apart faster than we can measure. These aren't just gaps in knowledge, they are cosmic riddles written into the fabric of reality itself. Take dark matter, for example. It's everywhere, weaving through galaxies like invisible scaffolding, holding stars together with its gravitational pull. Yet despite making up nearly 85% of the universe's matter, we've never directly seen it. Our telescopes are useless here. Dark matter doesn't emit, reflect, or absorb light. It's like trying to study a shadow by shining a flashlight at it. The harder we look, the more elusive it becomes, and that's the essence of the cosmic veil. The more we learn, the more we realize how much we're missing. Then there are quasars, blazing beacons from the early universe, pumping out enough energy to outshine entire galaxies. They're powered by supermassive black holes, but how they formed so quickly after the Big Bang remains a puzzle. Even stranger are fast radio bursts, cosmic signals so powerful they release more energy in milliseconds than our sun does in weeks. Some repeat at random intervals, while others vanish without a trace. Are they colliding stars, alien messages, or something we haven't even imagined yet? The cosmic veil reminds us that the universe loves a good mystery. Every time we peel back one layer, another appears, stranger than the last. It's what drives astronomers to build bigger telescopes, physicists to dream up wilder theories, and all of us to keep staring at the night sky, wondering what else is out there, just beyond our reach. Dark matter is the universe's greatest ghost story, an unseen force sculpting galaxies, bending light, and holding the cosmos together without ever revealing itself. Think of it like the wind. You can't see it, but you see its effects everywhere. Trees sway, leaves scatter, and storms form, all because of something invisible. In the same way, dark matter's gravitational grip shapes the motion of stars, warps the fabric of space-time, and even determines where galaxies cluster. Without it, the universe as we know it would fly apart. Yet after decades of searching, we still don't know what it actually is. Here's how bizarre this gets. All the atoms, planets, and stars we can observe, everything made of the familiar protons, neutrons, and electrons, account for less than 5% of the universe's total content. Dark matter makes up roughly 27%. That means for every visible galaxy spinning in the night sky, there's 5 times more mass lurking in the shadows, tugging at the cosmos from behind the scenes. Scientists first stumbled onto this mystery in the 1930s, when astronomer Fritz Zwicky noticed galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. It was as if invisible hands were keeping them from flying apart. So how do you study something you can't see? Astronomers have gotten creative. One method, called gravitational lensing, relies on Einstein's theory that massive objects bend light. When dark matter's gravity distorts the light from distant galaxies, it creates eerie, stretched-out mirages in space like cosmic fingerprints. Another approach involves ultra-sensitive detectors buried deep underground, shielded from cosmic rays, waiting for the faintest tremor of a hypothetical dark matter particle colliding with ordinary matter. Experiments like these have ruled out some possibilities, but the leading candidate, weakly interacting massive particles, or WIMP, remains frustratingly out of reach. And then there's the wild card. What if dark matter isn't a particle at all? Some theorists suggest it could be primordial black holes, forged in the chaos of the early universe. Others propose modifications to gravity itself, arguing that Einstein's equations might need tweaking on cosmic scales. The truth is, every time we think we're close to an answer, dark matter throws another curveball. Take the missing satellites problem, for example. Supercomputer simulations predict thousands of small dark matter clumps orbiting our Milky Way, yet we've only spotted a handful of dwarf galaxies in those locations. It's as if the universe left us a jigsaw puzzle with half the pieces hidden. This isn't just academic curiosity. Unraveling dark matter could rewrite the rules of physics, revealing dimensions or forces we never imagined. It might even hold clues to the universe's ultimate fate, whether it will expand forever, collapse back on itself, or tear apart in a big rip. For now, dark matter remains the ultimate cosmic tease, everywhere and nowhere, felt but not seen, the silent architect of everything. And that's what makes it so thrilling. The universe loves a good mystery, and dark matter might just be its masterpiece. If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force ripping them apart, an anti-gravity that's stretching the cosmos faster than anyone expected. Picture blowing up a balloon with dots on its surface. As the balloon expands, the dots move away from each other. Now imagine someone suddenly starts blowing harder, making the dots rush apart even faster. That's dark energy in action. It's not just expanding the universe, it's accelerating that expansion, defying gravity's pull in a way that left even Einstein stunned. When astronomers first discovered this cosmic speed-up in the late 1990s, it sent shockwaves through the scientific community. By measuring distant supernova exploding stars that serve as cosmic yardsticks, they realized the universe wasn't just growing. It was growing faster, as if some unseen hand kept pressing the gas pedal. That hand, we now know, is dark energy, making up a staggering 68% of all the energy in the cosmos. Unlike dark matter, which tugs galaxies into clusters, dark energy works in reverse, pushing everything apart so forcefully that one day, distant galaxies might vanish beyond an unreachable horizon. But what exactly is this force? The leading theory suggests dark energy is woven into the fabric of space itself, a property Einstein once called the cosmological constant. Empty space, according to quantum physics, isn't truly empty. It crackles with virtual particles popping in and out of existence, generating an energy that could drive expansion. But here's the catch. When scientists calculate how much energy this quantum activity should produce, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science history. This glaring discrepancy has led to wilder possibilities like phantom energy, a hypothetical dark energy variant that grows denser over time. If real, it could eventually shred galaxies, stars, even atoms in a catastrophic Big Rip. Or perhaps dark energy hints at extra dimensions, with gravity leaking into unseen realms. The James Webb Space Telescope is now hunting for clues, studying ancient galaxies to map how expansion has changed over billions of years. One thing's certain: dark energy forces us to confront profound questions. Will the universe expand forever, fading into cold isolation? Or will dark energy's grip weaken, allowing gravity to pull everything back in a big crunch? For now, it remains one of cosmology's deepest puzzles, a reminder that the cosmos is stranger and more dynamic than we ever imagined. Black holes aren't just cosmic vacuum cleaners. They're nature's most extreme laboratories, bending the rules of reality in ways that still baffle physicists. Picture space-time as a stretchy rubber sheet. Now drop a bowling ball onto it. That deep dent where the ball sits, that's essentially what a black hole does to the fabric of the universe, creating a gravitational well so steep that once anything crosses the event horizon, the point of no return, there's no coming back. Not even light can climb out, but here's where it gets wild. What happens inside that darkness might rewrite everything we know about physics. Take singularities, the mysterious hearts of black holes where gravity becomes infinite and space-time curves into oblivion. Our current laws of physics simply break down here. Einstein's equations suggest matter gets crushed to an infinitely dense point. But infinity isn't something that exists in nature. It's a sign that we're missing a crucial piece of the puzzle. Some theorists think quantum mechanics could rescue us from this mathematical nightmare, proposing that singularities might be replaced by quantum fuzzballs, or loops of energy that prevent true infinite density. Others speculate these cosmic whirlpools might be gateways, funneling matter into white holes, hypothetical exits where energy gushes back out into another universe. Imagine a cosmic drain that doesn't just swallow water but spits it out into another bathtub entirely. Recent breakthroughs have given us unprecedented glimpses into these enigmas. The first ever image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, revealed a fiery ring of light bending around the abyss of Messier 87's supermassive black hole. Then there are gravitational waves, ripples in space-time detected when black holes collide. These collisions release more energy than all the stars in the observable universe combined, yet they happen in complete silence, shaking the cosmos like a drumhead. Each detection peels back another layer of mystery, showing us black holes aren't static monsters but dynamic, spinning beasts that can eject jets of plasma at nearly light speed. Could black holes be cosmic shortcuts? The idea of wormholes, tunnels through space-time, often pops up in sci-fi, but it's rooted in real math. Einstein and physicist Nathan Rosen once theorized that black holes might connect to distant points in the universe or even alternate realities. The catch: anything passing through would likely get shredded by tidal forces or crushed by shifting physics. Still, some models suggest rotating black holes, called Kerr black holes, might have gentler interiors where matter could survive the trip. Of course, no one's volunteering to test that theory firsthand. What truly boggles the mind is how black holes might hold clues to unifying relativity and quantum mechanics, the holy grail of physics. At their cores, these objects pack the extremes of both theories into one nightmare puzzle. Studying them could reveal whether space-time is pixelated at the tiniest scales, or if information that falls into a black hole truly vanishes. A paradox Stephen Hawking wrestled with for decades. Every new observation, from swirling plasma patterns to the faint echoes of colliding black holes, brings us closer to answers, and that's the thrill of it. Black holes aren't just cosmic oddities, they're keys to unlocking the universe's deepest secrets, hidden behind the ultimate cosmic veil. Neutron stars are nature's ultimate pressure cookers, cosmic objects so dense they squeeze the mass of an entire sun into a space no bigger than Manhattan. Picture taking Mount Everest and compacting it into a sugar cube. That's the kind of crushing gravity at work here, where atoms get smashed so violently that electrons merge with protons, leaving behind a seething ocean of neutrons. The result: a single teaspoon of this star stuff would weigh over 1 billion tons on Earth. But the real magic happens when these stellar corpses start spinning. Some neutron stars become pulsars, cosmic lighthouses that beam radiation across the galaxy with metronome-like precision. The Crab pulsar, for example, spins 30 times every second, sending out flashes of light and radio waves so regular they rival atomic clocks. Then there are magnetars, the universe's unrivaled magnetic heavyweights. Their fields are 1,000 trillion times stronger than Earth's, so powerful they could wipe a credit card clean from halfway across the solar system. In 2004, a magnetar 50,000 light-years away released a burst of energy that briefly outshone the full moon, all from a quake on its crust no thicker than a fingernail. But what's really happening inside these ultra-dense orbs? At their cores, pressures might be so extreme that neutrons themselves break apart into a soup of quarks, the fundamental building blocks of matter. This could create quark stars, a hypothetical phase even stranger than neutron stars. Some researchers speculate that certain unusual cosmic explosions, like fast radio bursts, might be the birth cries of these exotic objects. Others wonder if quark matter could form strange stars, where quarks reconfigure into bizarre, stable patterns never seen on Earth. Neutron stars also serve as cosmic laboratories for testing Einstein's theories. Their immense gravity bends light so dramatically that we can see their backs from the front, a phenomenon called gravitational lensing. When two neutron stars collide, they don't just create fireworks, they forge gold, platinum, and other heavy elements in a process called rapid neutron capture. The gravitational waves from one such collision, detected in 2017, confirmed that these events are the universe's primary jewelry stores. What makes neutron stars truly captivating is how they straddle the line between the familiar and the unfathomable. They're made of particles we know, yet they behave in ways that defy intuition. Some pulse like clockwork, others erupt without warning, and a few might hide portals to new states of matter. Every observation peels back another layer, revealing just how inventive and how utterly strange the cosmos can be when pushed to its limits. Fast radio bursts are like the universe playing an interstellar game of Morse code, blasts of energy so powerful they outshine entire galaxies, yet so brief they're over before you can blink. Lasting just thousandths of a second, these cosmic flashes pack more energy than the sun emits in days, sometimes even weeks. And here's what makes them truly baffling. They're coming from galaxies billions of light years away, meaning whatever's producing them is unleashing unimaginable forces across cosmic distances. The first fast radio burst was discovered by accident in 2007, buried in old telescope data. Astronomers initially dismissed it as a glitch until more started appearing. Now, with sensitive arrays like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, we're detecting them almost daily. Some burst just once and vanish without a trace. Others, like FRB 1211-2, repeat at erratic intervals, flickering on and off like a cosmic lighthouse with a broken switch. So what's causing these titanic sparks? Theories range from the dramatic to the downright speculative. One leading idea points to magnetas, those ultra-magnetic neutron stars we discussed earlier. A sudden starquake or magnetic snap could unleash a burst so intense it ripples across the cosmos. Then there's the Blitzar hypothesis. Imagine a supermassive neutron star just barely holding itself together until, pop, its own gravity overwhelms it, collapsing into a black hole in a final, brilliant radio scream. But not all explanations are so apocalyptic. Some scientists entertain the wild possibility that repeating bursts could be signatures of advanced civilizations. Picture a distant alien race powering interstellar light sails with planet-sized transmitters. Or perhaps these bursts are accidental cosmic byproducts of technology we can't yet fathom. While extraterrestrial origins remain a long shot, the sheer weirdness of these signals forces us to consider every angle. What's truly fascinating is how fast radio bursts are helping map the universe's hidden scaffolding. As these pulses race across space, they interact with the sparse gas between galaxies, slowing ever so slightly. By measuring these delays, astronomers can weigh the universe's missing matter, the invisible atoms hiding in cosmic voids. It's like using lightning flashes to study the atmosphere, but on a galactic scale. Each new detection adds another piece to the puzzle. Some bursts arrive with a telltale twist in their radio waves, hinting at turbulent magnetic fields near their source. Others come with X-ray counterparts, suggesting violent collisions or eruptions. With every clue, we're not just solving the mystery of these bursts, we're piecing together a deeper understanding of how energy, matter, and even life itself might traverse the cosmos. One thing's certain, in a universe full of whispers, fast radio bursts are the screams we can't ignore. Somewhere in the depths of space, an invisible hand is pulling our galaxy, along with hundreds of thousands of others toward a point we can't even see. This is the Great Attractor, a gravitational anomaly so powerful it bends the motion of entire galaxies like leaves caught in a cosmic river. Picture throwing a handful of confetti into the wind, only to watch every piece drift mysteriously toward the same shadowy corner of the room. That's essentially what's happening across our galactic neighborhood, with everything from the Milky Way to distant galaxy clusters sliding toward this hidden focal point. What makes this enigma even stranger is its location. Nestled roughly 250 million light-years away in the direction of the Centaurus constellation, the Great Attractor lies directly behind the thick dust and stars of our own galaxy's disk, a region astronomers call the zone of avoidance because it's notoriously difficult to observe. It's like trying to spot a lighthouse through a blizzard. For decades, this cosmic blind spot kept the Great Attractor's true nature shrouded in mystery. Early measurements in the 1970s revealed our local galaxies weren't just drifting apart with the universe's expansion, they were all sliding sideways, tugged by something colossal. But what? The leading theory suggests the Great Attractor is a dense knot of matter, a supercluster of galaxies weighing in at roughly 100 quadrillion times the mass of our Sun. The Norma cluster sits at its heart, a bustling metropolis of galaxies bound together by gravity. But here's the twist, even this immense structure might not be the full story. Recent observations hint that the Great Attractor itself is being pulled towards something even larger, a mind-boggling concentration of mass nicknamed the Shapley supercluster, over 650 million light-years away. It's as if we've discovered a river's current only to realize it's part of a vast, invisible ocean. Could dark matter be the hidden architect? Simulations show the Great Attractor's gravity can't be explained by visible galaxies alone. Vast reservoirs of dark matter might be weaving through this region, amplifying its pull like an unseen anchor. Some researchers speculate there could be exotic structures at play, cosmic filaments where dark matter flows in rivers, or even primordial defects in space-time left over from the Big Bang. The hunt for answers is pushing telescopes to their limits. Infrared surveys like those from the Spitzer Space Telescope peer through the Milky Way's dust, while radio arrays map hydrogen gas swirling in the attractor's grasp. Each new dataset chips away at the mystery, revealing more galaxies, more mass, and more questions. One thing's clear, the Great Attractor isn't just a destination. It's a signpost pointing to the universe's hidden scaffolding, where gravity's whisper shapes the fate of galaxies on scales we're only beginning to comprehend. If you could peer into the void between stars with a microscope powerful enough to see the fabric of reality itself, you'd witness chaos, a boiling ocean of particles popping into existence and vanishing again in less than a heartbeat. This isn't science fiction. It's the quantum vacuum, where empty space crackles with more energy than all the matter in the universe combined. Far from being a tranquil nothingness, the vacuum is a dynamic arena where so-called virtual particles, electron pairs, quarks, even entire atoms borrow energy from nowhere, exist for unfathomably short instants, then disappear back into the void. The implications are staggering. This quantum froth might hold answers to some of cosmology's biggest mysteries. Take the Casimir effect. Place two uncharged metal plates incredibly close together in a vacuum, and they're inexplicably pulled toward each other. Why? Because the space between the plates is too narrow for certain virtual particles to form, while the ocean of particles outside continues unchecked, creating a pressure differential. It's like lowering a divider into a stormy sea. The waves outside push harder than the calm within, nudging the plates together. This bizarre phenomenon, first measured in the 1990s, is direct proof that the vacuum is alive with transient energy. But here's where it gets wild. Some theorists suggest this vacuum energy could be the engine behind dark energy, that mysterious force accelerating the universe's expansion. If the quantum vacuum constantly generates repulsive energy, it might explain why galaxies are flying apart faster and faster. There's just one problem. When physicists calculate how much energy the vacuum should produce, the numbers are off by a factor of 1 followed by 120 zeros. It's the most embarrassing mismatch in science, hinting that we're missing something fundamental about how quantum fields interact with gravity. Others propose even more radical ideas. Could these flickering particles be glimpses of parallel universes? In the multiverse hypothesis, every virtual particle might represent a momentary bridge to another reality, a place where different physical laws hold sway. Or consider zero-point energy, the notion that even at absolute zero, the vacuum thrums with residual motion. Harnessing this energy remains science fiction, but its existence challenges our definition of nothing. The quantum vacuum reminds us that reality's building blocks are anything but static. Every cubic centimeter of space, no matter how empty it seems, is a maelstrom of creation and annihilation, a dance of energy that might hold secrets to the universe's birth and its ultimate fate. As experiments grow more precise, from atom smashers probing Planck-scale physics to space telescopes mapping dark energy's grip, we're inching closer to answers. One thing's certain, the cosmos is far stranger than a mere void. It's a seething, shimmering frontier where nothing is ever truly still. White holes stand as one of the most tantalizing what-ifs in modern cosmology, the yin to a black hole's yang, where instead of an all-consuming abyss, you'd face a cosmic fire hose blasting matter and energy into the universe at impossible speeds. Picture a black hole running backward in time, where gravity's grip becomes an unstoppable push, where the event horizon isn't a point of no return but a boundary nothing can cross from the outside. The math allows for such objects. Einstein's equations describing black holes are symmetric, meaning white holes pop out as valid solutions just by flipping the sign on time. Yet for all their theoretical elegance, not a single confirmed white hole has ever been spotted. So where are they hiding? One compelling idea suggests white holes could be the afterlife of black holes. In-loop quantum gravity, a theory aiming to bridge relativity and quantum mechanics. Black holes might not crush matter into singularities forever. Instead, at some point, the collapsing star could rebound in a titanic reversal, transforming into a white hole. The transition would take longer than the current age of the universe for a typical black hole, but primordial black holes from the Big Bang's chaos could have already made the switch. If so, we might be surrounded by ancient white holes quietly spraying energy into space like cosmic sprinklers. Then there's the more explosive possibility. What if gamma ray bursts? Those blinding flashes of high-energy radiation detected across the cosmos are actually white holes being born. Some models show that when a white hole forms, it doesn't just gently exhale matter. It detonates with enough force to outshine galaxies, potentially matching the energy profiles of these mysterious bursts. Even stranger, a handful of physicists speculate that the Big Bang itself could have been a supermassive white hole event, with our universe erupting from the remains of a collapsed spacetime in another reality. It's a dizzying thought that every galaxy, star, and planet might trace back to a white hole's outburst. But why is evidence so scarce? Part of the challenge is that white holes defy thermodynamics. They'd need to generate energy from nowhere, violating the law of conservation. Others argue they might disguise themselves as mundane cosmic phenomena. For example, certain types of active galactic nuclei, bright cores of distant galaxies, exhibit jets of plasma that behave suspiciously like white hole ejections. There's also the black hole to white hole tunneling hypothesis, where quantum fluctuations could create microscopic shortcuts between the two, briefly turning black holes into white holes before they evaporate via Hawking radiation. The search continues. New gravitational wave detectors might catch the signature tremors of a white hole's birth, while next-generation telescopes could spot unusual radiation patterns betraying their presence. Whether they're relics of dying black holes, engines behind cosmic cataclysms, or mere mathematical ghosts, white holes remind us that the universe's strangest possibilities often lurk just beyond the edge of observation, waiting for physics to catch up to imagination. The holographic principle flips reality on its head. What if everything we see, touch, and experience is just an illusion? A shimmering mirage projected from some distant cosmic surface. Imagine stepping closer to a movie screen until the individual pixels blur into a seamless image. Now scale that up to universal proportions. Every galaxy, every atom, even your own thoughts might be nothing more than data etched onto a two-dimensional boundary at the edge of existence. It sounds like science fiction, but this theory emerges from the cold, hard math of black hole physics. The idea first took shape in the 1990s when physicists studying black holes stumbled onto a paradox. According to quantum mechanics, information can never be destroyed, yet when matter falls into a black hole, it seemingly vanishes without a trace. The solution. Maybe the information isn't lost at all. Maybe it's smeared across the black hole's event horizon like ink on parchment, preserving every detail of what fell in. From there, the leap to a holographic universe wasn't so far-fetched. If a black hole's contents could be encoded on its surface, why not the entire cosmos? Here's where it gets wild. The mathematics suggests that the three-dimensional world we inhabit with its mountains, oceans, and stars could be a projection from a flat, two-dimensional realm. Gravity, in this view, isn't a fundamental force but a side effect of this cosmic encoding, like shadows cast by a flickering light. The holographic principle doesn't just rearrange reality, it could bridge the chasm between quantum mechanics and general relativity, two theories that have stubbornly refused to unite for a century. But how do you test something this abstract? One approach involves scouring the cosmic microwave background, the afterglow of the Big Bang, for telltale pixelation. If the universe is a hologram, there might be subtle noise in this ancient light, evidence of an underlying granularity to space-time. Another avenue explores quantum entanglement, the eerie connection between particles that Einstein called spooky action at a distance. Entangled particles might be linked because they're projections of the same deeper code, like two characters in a movie sharing the same script. Skeptics argue that the holographic principle is more philosophy than physics, an elegant idea without experimental proof. Yet recent lab experiments have simulated holographic universes using ultra-cold atoms and lasers, observing behaviors that mirror the theory's predictions. Meanwhile, astronomers are developing instruments sensitive enough to detect holographic fuzziness in distant quasars. Whether the holographic principle holds up or not, it forces us to confront a humbling possibility. Reality might be far stranger and far more interconnected than our senses suggest. The universe has always been full of surprises, and this could be its greatest sleight of hand, yet a cosmic magic trick where the stage, the audience, and even the magician are all part of the illusion. What if every choice you've ever made, every path taken or left behind exists simultaneously in an endless sea of alternate realities? The multiverse theory isn't just a sci-fi trope. It's a serious scientific proposition that our cosmos might be one tiny bubble in an infinite froth of universes, each with its own unique rules. Picture a cosmic foam where new universes constantly sprout from the fabric of space-time, some with gravity 10 times stronger, others where light moves at a crawl, and a few where life as we know it could never exist. This isn't wild speculation, it's a natural extension of inflationary cosmology, the leading theory for how our universe expanded from a speck to cosmic vastness in less than a blink after the Big Bang. The math behind this is both elegant and mind-bending. Inflation suggests that certain quantum fluctuations in the early universe could have triggered eternal expansion, creating pockets where space-time stretches forever. Each pocket becomes its own isolated universe, with physical constants randomly shuffled. String theory takes it further, proposing that higher dimensional brains could collide like sheets in a cosmic laundry pile, birthing new universes with every impact. Suddenly, the fine-tuning of our universe, the precise balance that allows stars, planets, and life to exist starts to make sense. If there are infinite variations, some are bound to hit the cosmic jackpot. But how do we test something so seemingly untouchable? Some physicists search for bruises in the cosmic microwave background anomalies that might reveal collisions with neighboring universes. Others look for gravitational echoes from brain collisions, or even deviations in the behavior of fundamental particles that could hint at unseen dimensions. Then there's the quantum multiverse, where every decision spawns parallel timelines. In this view, you might be a doctor in one universe, a musician in another, and somewhere out there, a version of you is reading these words backward in a reality where time flows the opposite direction. Critics argue the multiverse is more metaphysics than physics, an idea so flexible it can't be falsified. Yet supporters counter that it's no different from early debates about atoms or black holes. Just because we couldn't see them didn't mean they weren't real. Whether the multiverse exists or not, it forces us to confront staggering questions. Are we one cosmic accident among countless failures, or is there a deeper structure that connects all possible realities? The answer might lie beyond the veil of our observable universe, in a realm where every possibility is inevitable, and the word alone loses all meaning. Einstein shattered the illusion of a universal clock when he revealed time's elastic nature, stretching, compressing, and warping under the influence of gravity and velocity. Picture two identical clocks, one placed on Earth's surface, the other launched into orbit. After a year, the orbiting clock would tick slightly ahead, not because it's faulty, but because time itself flows faster where gravity's grip weakens. This phenomenon, called time dilation, isn't just a quirk of relativity. It's a fundamental feature of the cosmos, with consequences far stranger than fiction. Take the supermassive black hole at our galaxy's core, Sagittarius A. If you could hover near its event horizon, where gravity bends space-time into a near standstill, a single hour for you might equate to years passing on Earth. The closer you get to that point of no return, the more time distorts, like molasses dripping slower and slower until it almost freezes. Astronomers have actually observed this effect on stars orbiting the black hole. Their light stretches into lower frequencies, a telltale sign of time dragging under extreme gravity. But here's the mind-bending question. If time can slow to a crawl, could it ever stop entirely or reverse? The equations allow for it. At the singularity inside a black hole where density becomes infinite, time's arrow might theoretically snap. Some models suggest that under these conditions, the distinction between past and future blurs, opening the door to closed time-like curves, paths through space-time that loop back on themselves. While this doesn't quite mean time travel as Hollywood imagines it, it hints that the universe's chronological fabric is far more malleable than we've dared to assume. Then there's velocity's role in twisting time. Particles accelerated to near-light speeds in Earth's colliders experience time dilation so extreme that their decay rates slow dramatically. A muon that should vanish in microseconds can outlive its expected lifetime by factors of hundreds when racing through a detector at 99.9% the speed of light. Scale this up, and a hypothetical starship crew traveling at such velocities could return to Earth to find centuries have passed at home while they've aged only years. The universe, it seems, has no master clock, just countless local versions, each ticking to its own rhythm. What does this mean for time's true nature? Quantum physicists speculate that time might emerge from something deeper, a cosmic network of entangled events where cause and effect are fluid. Experiments with entangled particles already show that quantum systems can behave as if they're outside time, reacting to each other instantaneously across vast distances. Could time itself be a kind of illusion, a side effect of how we perceive the universe's underlying structure? From black holes bending clocks to particles defying decay, time dilation forces us to confront a startling truth. the universe operates less like a rigid machine and more like a symphony where each note, each moment resonates at its own tempo. The deeper we probe, the clearer it becomes that time isn't just something we measure. It's something the universe sculpts moment by moment in ways we're only beginning to decipher. The universe is unimaginably vast, 2 trillion galaxies, each brimming with hundreds of billions of stars, countless planets swirling in habitable zones. Given those numbers and the 13.8 billion years since the Big Bang, intelligent life should have emerged over and over again. So why does the cosmos feel so eerily silent? This is the Fermi Paradox, the unsettling gap between the high probability of alien civilizations and the total lack of evidence they exist. Physicist Enrico Fermi first posed the question bluntly in 1950, where is everybody? One possibility is tragically simple: maybe civilizations don't last. The Great Filter theory suggests some catastrophic barrier prevents life from progressing to interstellar travel. It could lie in our past. Perhaps the leap from single cell to complex life is astronomically rare. Or worse, it awaits us in the future. Nuclear war, environmental collapse, or runaway artificial intelligence could snuff out advanced societies before they spread beyond their home world. The chilling implication: if the filter is ahead of us, humanity might be approaching its own existential dead end. But there are less grim explanations. Advanced civilizations might deliberately avoid contact, treating Earth like a nature preserve in a galactic zoo. The prime directive hypothesis imagines aliens withholding their presence until we reach a certain technological or ethical maturity, like parents letting a child learn to walk without interference. Others propose that we're simply searching the wrong way. Our radio telescopes listen for deliberate signals, but what if everyone's moved beyond radio, communicating via neutrino beams or quantum entanglement? It's like trying to spot airplanes by scanning for smoke signals. Then there's the cosmic scale itself. Even if civilizations are out there, space is so vast that signals might take millennia to reach us or arrive when no one's listening. Imagine a distant alien broadcast hitting Earth during the Cretaceous period, unheard by anything but dinosaurs. Alternatively, we might be living in a cosmic backwater, far from the bustling interstellar highways where civilizations trade and communicate. The Fermi Paradox doesn't just challenge our search for aliens, it holds up a mirror to humanity. Are we the universe's firstborn, destined to spread life through the void? Or are we latecomers, wandering the ruins of civilizations that rose and fell billions of years ago? Every silent star deepens the mystery, reminding us that the greatest enigma might not lie in the cosmos, but in our own uncertain place within it. Cosmic strings are like the universe's stretch marks, thin, unimaginably dense scars left over from the fiery birth of everything. If space-time is a smooth fabric, these strings would be its frayed edges, remnants of the violent phase transitions that occurred a fraction of a second after the Big Bang. Picture the universe cooling from an unfathomable heat, like molten glass solidifying, but as it hardened, tiny cracks formed, defects where the fabric of reality didn't quite stitch together seamlessly. These cracks could have stretched into cosmic strings, thinner than a proton but with the mass of a mountain range packed into every inch, humming with the tension of a universe trying to hold itself together. What makes them so fascinating is how they'd warp the cosmos. A cosmic string drifting through space wouldn't just tug on nearby matter, it would slice through space-time itself, creating gravitational lenses that distort light from objects behind it. Imagine looking at a galaxy and seeing it duplicated, not by a black hole's gravity, but by an invisible thread cutting across the sky. Some theories suggest these strings could even form loops, vibrating like guitar strings and emitting faint gravitational waves, ripples in space-time we might detect with observatories like LIGO. But why haven't we found one yet? Cosmic strings would be nearly invisible, only betraying their presence through subtle gravitational tricks or the rare, explosive snap of a breaking loop. Some researchers are scouring the cosmic microwave background for telltale temperature fluctuations, fingerprints of a string's passage. Others hunt for bizarre double images of distant quasars, the kind that couldn't be explained by ordinary gravity. There's even a wild possibility that cosmic strings could explain some of the universe's largest structures, acting as cosmic scaffolding that guided the formation of galaxy clusters in the early universe. The most mind-bending implication: if these strings exist, they might not just be relics, they could be active players in the cosmos. Certain models suggest that cosmic strings could collapse into black holes or even spawn new universes, like bubbles forming along a crack in ice. Others propose they're tangled up in dark matter, their gravitational pull shaping the invisible halos around galaxies. Whether they're fossils or cosmic architects, one thing's certain: finding a cosmic string would be like discovering the universe's blueprints, written in a language of gravity and geometry we're only beginning to decode. For now, they remain one of cosmology's most tantalizing what-ifs, a reminder that the early universe might have left behind more than just light and matter. It might have etched its secrets into the very fabric of space, waiting for us to trace the scars. Gamma-ray bursts are the universe's ultimate tantrums, blinding flashes of energy so intense they momentarily outshine everything else in the cosmos. Imagine squeezing the sun's entire lifetime output of radiation into just a few seconds, then focusing it into a narrow beam. That's the raw, unfiltered power of these cosmic detonations. First detected by military satellites in the 1960s, initially mistaken for nuclear tests, these bursts come in two flavors. The short ones, lasting less than 2 seconds, are thought to be the death cries of colliding neutron stars, those ultra-dense stellar corpses we discussed earlier. The long bursts, stretching minutes, likely mark the violent birth of black holes as massive stars collapse under their own weight. What makes them truly terrifying is their efficiency. A typical burst converts more energy in seconds than our sun will produce in 10 billion years. Some originate from galaxies billions of light years away, yet their afterglows remain visible for weeks. The record holder, GRB 080319b, erupted from a galaxy 7.5 billion light-years distant, so powerful it briefly altered Earth's ionosphere. But here's the chilling part: if one occurred within our galactic neighborhood, say a few thousand light-years away, its high-energy radiation could strip our ozone layer, trigger mass extinctions, and bathe the planet in deadly ultraviolet light. Evidence suggests this might have happened before. A gamma-ray burst may have contributed to the Ordovician extinction 450 million years ago, wiping out nearly 85% of marine species. Yet for all their destructive potential, these bursts are also cosmic Rosetta Stones. Their light carries fingerprints of the distant universe, revealing the composition of interstellar gas and the rate of cosmic expansion. When two neutron stars collided in 2017, producing both a gamma-ray burst and gravitational waves, it proved these events forge heavy elements like gold and platinum. Each detection peels back another layer of mystery, showing us how the universe transforms chaos into creation. The hunt for answers continues. Satellites like Swift and Fermi scan the skies for bursts, while robotic telescopes swivel to capture their fading afterglows. Some researchers even speculate that certain bursts could be artificial hypothetical alien power sources or weapons. While that's a long shot, it underscores how these phenomena push the limits of what we thought possible. Gamma-ray bursts don't just illuminate the cosmos, they force us to confront how small and fragile we truly are in a universe capable of such breathtaking violence. The cosmic microwave background should be the universe's fingerprint, a near-perfect snapshot of the infant cosmos, its faint glow of radiation spread evenly in all directions. Yet when scientists mapped this ancient light with unprecedented precision, they stumbled upon something unsettling. The data revealed a bizarre alignment, a mysterious axis where temperature fluctuations seemed to coordinate across vast distances, as if the universe itself had a preferred direction. Astronomers jokingly called it the axis of evil, but the implications are anything but humorous. This anomaly shouldn't exist. According to our best theories, the early universe was a chaotic, seething place with no preferred orientation. So why does the CMB look like it's been combed in one particular direction? One possibility is that we're seeing echoes from before the Big Bang. Some models of cyclic cosmology suggest our universe might be one in a series, with each new cycle inheriting faint imprints from its predecessor. The axis of evil could be a cosmic bruise, a remnant of some colossal collision or structure from a prior iteration of reality. Even stranger, it might hint at a multiverse, where the gravitational tug of a neighboring universe just beyond our observable horizon is subtly warping space-time like a shadow on the wall. Then there's the chance it's all a grand illusion, a statistical fluke magnified by the way we process CMB data. Our galaxy's own motion creates a dipole pattern in the microwave background, and some researchers argue that incomplete correction for this effect might artificially enhance the anomaly. Others propose that quantum fluctuations during inflation, the universe's explosive early growth spurt, could have left behind unexpected large-scale correlations. But if the axis of evil is real, the consequences are profound. It would mean the universe isn't just lopsided, it's fundamentally oriented, challenging the cosmological principle that no place or direction in space is special. Future telescopes, like the European Space Agency's Euclid mission, aim to test this by mapping the distribution of galaxies to see if they, too, align with this eerie cosmic axis. Until then, the mystery lingers, a silent reminder that even our most refined models of the cosmos might be missing something monumental. The universe, it seems, still has a few tricks up its sleeve. Oumuamua wasn't just another space rock, it was the first confirmed visitor from another star system, streaking through our cosmic neighborhood at nearly 200,000 miles per hour. Discovered in October 2017 by astronomers at the Pan-STARRS telescope in Hawaii, this mysterious object defied every expectation. Its shape alone was bizarre, a tumbling, cigar-like structure roughly 10 times longer than it was wide, spinning chaotically as it hurtled past the sun. But what really sent scientists into a frenzy was its behavior. Instead of slowing down as expected after its closest approach to the sun, Oumuamua sped up as if propelled by some unseen force. At first, researchers assumed it was a comet, venting gases that acted like a natural thruster, yet no tail or coma. The classic halo of dust and gas around comets was visible. Others suggested it might be a rare type of hydrogen iceberg, evaporating silently in sunlight. Then came the wilder theories. Harvard astronomer Avi Loeb famously proposed that Oumuamua's acceleration and unusual shape could hint at artificial origins, perhaps a light sail from an alien civilization drifting between the stars. While most scientists remained skeptical, the mere possibility forced us to confront a humbling truth. After centuries of staring at the sky, we still don't know what's passing through our own backyard. The closer we looked, the stranger Oumuamua became. Spectral analysis revealed its surface was unusually reflective, more like polished metal than the dull, carbon-rich coatings of most asteroids. Its trajectory suggested it had wandered the Milky Way for hundreds of millions of years before stumbling upon our solar system, making it a pristine relic from an alien star system. Some astrophysicists speculate it could be a shard of a Pluto-like world, torn apart by gravitational forces far from here. Others wonder if it's a member of an unseen population of interstellar objects lurking in the darkness between stars. What makes Oumuamua so tantalizing isn't just its mystery, it's the realization that our solar system might be constantly buzzing with interstellar interlopers. New telescopes like the Vera Rubin Observatory, set to begin sweeping the skies in 2025, could soon spot dozens more. Each one would be a time capsule, carrying secrets from distant corners of the galaxy. Whether natural or artificial, Oumuamua was a cosmic wake-up call. The universe doesn't just whisper its secrets sometimes, it sends them hurtling right past us. The next time one comes knocking, will we be ready to listen? What if the universe is teeming with civilizations so advanced they've mastered energy on scales we can barely comprehend? That's the spine-tingling question behind the Kardashev Scale, a cosmic yardstick that ranks civilizations by their ability to harness power. Picture this. A Type 1 civilization has tamed every ounce of energy on its home planet, controlling weather, volcanoes, even earthquakes. A Type 2 has graduated to stellar engineering, building megastructures like Dyson spheres to siphon the full output of their sun. And a Type 3, they've achieved the unimaginable, commanding the energy of an entire galaxy, with technology that bends the laws of physics to their will. Right now, humanity hovers around a measly Type 0.73 on this scale. We're still burning fossil fuels, squabbling over resources, and barely tapping into the fraction of solar energy that reaches Earth. But the Kardashev Scale isn't just about grading our progress, it's a roadmap to the kind of cosmic company we might one day keep. Imagine a civilization millions of years ahead of us, one that treats stars as charging stations and black holes as power plants. Theoretical physicist Freeman Dyson once speculated that advanced beings might dismantle planets to build computational matrices the size of solar systems. Others suggest they could manipulate dark energy itself, turning the vacuum of space into a battery. The eerie part: if such civilizations exist, we might already be missing their signatures. A Type 3 society wouldn't communicate with primitive radio waves, they'd use neutrino beams or quantum entanglement, technologies we're only beginning to fathom. Their megastructures might emit waste heat in patterns we've mistaken for natural astrophysical phenomena. Some astronomers even propose that unexplained infrared glows from distant galaxies could be the exhaust fumes of their cosmic engines. Yet the Kardashev Scale also holds a mirror to our own future. To reach Type 1, we'd need to harness roughly 100,000 terawatts, equivalent to capturing all the sunlight hitting Earth. That's not just about solar panels, it's about mastering fusion, geothermal, and perhaps even zero-point energy. The leap to Type 2, that demands feats like stabilizing a star's fusion reactions or constructing a Dyson swarm, a constellation of energy collectors orbiting the sun. As for Type 3, well, that's the stuff of dreams, wormhole networks, warp drives, and the ability to rewrite the universe's operating system. The scale doesn't just measure energy, it measures imagination. Every time we scan the cosmos for signs of intelligence, we're implicitly searching for Kardashev's ghosts. Maybe they're out there, cloaked in technologies we can't yet perceive. Or maybe the scale is a warning. Civilizations that reach too high, too fast, might burn themselves out before they ever leave their cradle. Either way, the universe has left the lights on. The question is, who or what flipped the switch? Panspermia turns the origins of life into a cosmic detective story. What if Earth wasn't the starting point, but just one lucky stop on a galactic delivery route? Picture a comet, a frozen relic from the dawn of the solar system, plowing through space with its icy payload. Locked inside its frigid core, shielded from radiation by layers of rock and ice, microscopic hitchhikers could lie dormant for millions of years. Then, during a fiery plunge into Earth's early oceans, that ice melts, releasing its passengers into a warm, watery paradise. Suddenly, life isn't just an earthly accident. It's a universal inevitability, spread like pollen on the solar wind. The idea isn't as far-fetched as it sounds. We already know space is littered with organic molecules, amino acids found in meteorites, sugars swirling in interstellar clouds. In labs, scientists have exposed bacteria to the vacuum of space, and some, like the indestructible tardigrade, survived years of radiation and freezing temperatures. Even more compelling are the extremophiles on Earth, microbes thriving in boiling vents, acidic lakes, or deep underground. If life can flourish in these hellish corners of our planet, why not in the icy cracks of Europa or the methane rivers of Titan? Critics argue that panspermia just kicks the can down the road. It doesn't explain how life began, only how it might have moved. But supporters counter that the universe is vast and ancient. The raw ingredients for life could have formed in the turbulent nurseries of nebulae, then scattered like cosmic confetti during supernova. Some models even suggest that life-bearing rocks could escape a planet's gravity during asteroid impacts, becoming natural spacecraft ferrying biology between stars. The implications are staggering. If panspermia is real, life might be everywhere, waiting in the frozen shadows of moons, dormant in Martian soil, or drifting through the atmospheres of gas giants. A single microbe surviving the journey would mean the difference between a sterile universe and one brimming with possibility. Missions like NASA Europa Clipper or Japan's Martian moon sample return could soon turn speculation into evidence, hunting for telltale signs of alien biology in the ice. Whether panspermia holds the key to life's origins or not, it reshapes how we see our place in the cosmos. We might not just be inhabitants of Earth, we could be descendants of the stars, carrying stardust in our DNA and echoes of ancient interstellar voyages in every cell. The universe, it seems, doesn't just build worlds, it might sow them with life, one frozen traveler at a time. Black holes aren't just cosmic vacuum cleaners, they're information shredders, and that's the heart of one of physics' most heated debates. Imagine tossing a book into a fire. The pages burn, but the smoke and ash still carry traces of the ink, the binding, even the author's name. Now picture that book falling into a black hole. According to Einstein's general relativity, every detail, every word, every letter gets crushed into oblivion at the singularity, erased from existence. But quantum mechanics insists that information can never truly vanish. It might get scrambled, hidden, or transformed, but it can't be deleted. So who's right? The answer could rewrite our understanding of reality. Enter Stephen Hawking's bombshell discovery. Black holes aren't entirely black, they leak. Through a bizarre quantum quirk, pairs of particles flicker into existence at the event horizon. One falls in, while the other escapes as radiation, slowly bleeding the black hole's mass over eons until it vanishes entirely. This Hawking radiation solved one puzzle but created another. If the radiation is random thermal noise, where does the swallowed information go? It's like burning that book again, but this time the ashes contain no clues about its contents. Quantum purists revolted. If information is lost, the entire framework of quantum theory, with its precise predictability, collapses. The stakes couldn't be higher. Some theorists propose wild solutions like the holographic principle, where information isn't lost but smeared across the black hole's event horizon like a cosmic etch-a-sketch. Others suggest black holes might tunnel into white holes, regurgitating their contents in some distant future or alternate universe. Then there's the firewall hypothesis, a searing wall of energy at the event horizon that fries anything crossing it, preserving information by preventing it from ever reaching the singularity. Critics argue this violates relativity's prediction that falling into a black hole should feel like nothing at all, at least until the crushing begins. What's truly fascinating is how this paradox forces physics to confront its own limits. General relativity and quantum mechanics, our two most successful theories, clash spectacularly here. Resolving the paradox might require a theory of quantum gravity, a way to stitch space-time's fabric together with quantum rules. String theory and loop quantum gravity are contenders, but neither has delivered a knockout punch. Meanwhile, lab experiments with analog black holes, using sound waves in superfluid helium or light in optical fibers, are testing these ideas on tabletops. The deeper we dig, the stranger it gets. Some models suggest information escapes encoded in subtle quantum correlations within the Hawking radiation, like a message hidden in static. Others wonder if black holes are cosmic USB drives storing data in higher dimensions. One thing's certain, solving this puzzle won't just tell us what happens to a particle falling into a black hole. It'll reveal whether the universe itself is a vast, unbreakable code, or if some secrets truly disappear forever. What if everything around you, the stars, the air you breathe, even the thoughts in your head, weren't real but lines of code in an unfathomably powerful simulation? The simulation hypothesis isn't just sci-fi speculation. It's a serious argument that our universe might be an artificial construct, engineered by some advanced civilization with computing power beyond our wildest dreams. Think of it like this: if humanity can already create immersive virtual worlds with rudimentary AI and graphics, what could a civilization millions of years ahead of us achieve? They might not just simulate worlds, they could simulate entire universes, complete with conscious beings who never suspect they're living in someone else's program. The idea gained traction when philosopher Nick Bostrom laid out a chilling logical trilemma in 2003. Either 1, intelligent civilizations always go extinct before developing simulation technology. 2, they choose not to run ancestor simulations for ethical or practical reasons. Or 3, the unsettling possibility, we're almost certainly living in one. The math is simple. If even a fraction of civilizations survive to create simulations, the number of artificial minds would dwarf biological ones. Statistically, the odds tilt heavily toward us being simulated. But where's the evidence? Some point to quantum mechanics as potential glitches in the cosmic code. Take the double-slit experiment, where particles behave as waves or particles depending on whether they're observed. It's almost as if the universe is rendering reality only when needed to save processing power. Then there's the speed of light. Could it be a built-in limit to prevent the simulation from overloading? Even the pixelated nature of space-time at the tiniest scales, hinted at by quantum gravity theories, mirrors how video games break reality into discrete chunks. Of course, skeptics push back hard. Physicist Neil deGrasse Tyson quipped that if we are in a simulation, it's embarrassingly buggy. Why would advanced beings program mosquitoes or reality TV? Others argue the hypothesis is untestable by definition. If the simulation is perfect, how could we ever detect its seams? Yet some scientists are actively looking for anomalies. One team proposed searching for repeating patterns in cosmic rays, artifacts of a finite computational grid. Another suggested that quantum entanglement's spooky action might reveal limits in how the simulation processes information. The simulation hypothesis forces us to confront existential questions. If reality isn't fundamental, does consciousness lose meaning? Could glitches explain déjà vu or supernatural encounters? And if we're just data in a cosmic mainframe, what happens when the beings running it decide to shut it down? Whether you find the idea terrifying or exhilarating, one thing's certain: it turns the cosmic veil into a mirror. The deeper we probe, the more we're left wondering if the universe's code, who or what wrote it. Tachyons defy everything we think we know about speed and time. Unlike ordinary particles that inch closer to light speed only with tremendous energy, these hypothetical phantoms are born faster than light, slowing down as they gain energy, never dipping below that cosmic speed limit. Imagine a car that goes slower the harder you press the gas pedal, forever stuck in warp drive. Even stranger, Einstein's equations suggest tachyons might travel backward in time, their existence teasing us with the possibility of messages from the future or violations of cause and effect. The math behind these particles is as elegant as it is bizarre. In the 1960s, physicists realized that certain solutions to relativity's equations allowed for particles with imaginary mass, a mathematical term implying they'd accelerate past light speed effortlessly. String theory later provided a potential playground for them, extra dimensions curled up so tightly we'd never notice, where tachyons could flit between realities like ghosts through walls. Some models even propose they're the cosmic glue holding dark matter together, or the hidden mechanism behind quantum entanglement's spooky connections. But why haven't we detected them? Tachyons, if they exist, would leave eerie signatures, sudden bursts of Cherenkov radiation in a vacuum, or particles appearing to vanish before they're born. Experiments have hunted for these traces in cosmic rays and particle colliders, so far drawing blanks. Critics argue tachyons are mathematical mirages, artifacts of equations unmoored from reality. Yet the tantalizing possibility remains. What if we're not looking in the right way or the right dimension? The implications are dizzying. A tachyon-based communication system could send messages into the past, rewriting history with a single transmission. Interstellar travel might leapfrog light-speed barriers, using tachyons to warp spacetime like a sail catching the wind of higher dimensions. Of course, the paradoxes pile up fast. What stops a tachyon signal from altering the event that sent it, erasing its own existence? Some theorists suggest tachyons obey hidden rules, weaving through timelines without unraveling causality. Others think they're locked away in parallel universes forever beyond our reach. Whether phantom or future breakthrough, tachyons force us to confront the universe's deepest taboos. They're reminders that light speed might not be the ultimate barrier, just the edge of a frontier we've yet to cross. Until then, they linger at the intersection of imagination and physics, daring us to rethink the impossible. Imagine a universe that lasts forever, stretching across infinite time and space. Now consider this unsettling possibility. Given enough time, random quantum fluctuations could spontaneously assemble a fully conscious brain, complete with false memories of an entire life. These hypothetical entities, dubbed Boltzmann brains, aren't just science fiction. They're a nightmare scenario for cosmologists, forcing us to confront whether our own sense of reality might be an accident of physics. The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who first grappled with how order emerges from chaos. His work showed that in a vast enough cosmos, even the most improbable events, like all the air molecules in a room gathering in one corner, must eventually happen. Extend that logic to consciousness and you get Boltzmann brains, self-aware structures that flicker into existence from the void, convinced they're living in a real universe. The truly disturbing part, in an eternal universe, these phantom minds would vastly outnumber ordinary beings like us. Statistically, you're more likely to be a random fluctuation than an evolved organism. This isn't just abstract philosophy. The Boltzmann brain problem exposes a crisis in modern cosmology. If the universe is truly infinite, why don't we observe more of these freak occurrences? One escape hatch is the idea that our universe isn't eternal, that it began with the Big Bang and will eventually die in heat death, leaving too little time for Boltzmann brains to dominate. But even this leads to dizzying implications. Some theories suggest the Big Bang itself could be a quantum fluctuation, making our entire cosmos a temporary blip in an otherwise empty void. The debate gets stranger when quantum mechanics enters the picture. In the many worlds interpretation, every quantum decision spawns alternate realities. Could some branches of the multiverse be overrun by Boltzmann consciousness, while others remain real? Others propose that the very act of observation might stabilize reality, preventing these aberrations from forming. It's as if the universe knows it's being watched and behaves accordingly. What makes this paradox so gripping is how it turns the search for cosmic understanding into a hall of mirrors. Every time we think we've grasped the universe's true nature, the Boltzmann brain whispers, "But what if you're just a fleeting thought in the void?" Whether a thought experiment or a genuine threat to our models, it forces science to ask uncomfortable questions, not just about the cosmos, but about the nature of existence itself. The answers, if they exist, might lie beyond the limits of human comprehension. The Big Bang wasn't the beginning, it was a rebirth. Peel back the layers of cosmic history far enough, and you hit a wall of mystery. What, if anything, came before that fiery moment 13.8 billion years ago? The equations of general relativity break down at the singularity, leaving us staring into a void of possibilities. Some theories suggest our universe is just the latest chapter in an endless cycle of expansion and collapse, like a cosmic phoenix perpetually rising from its own ashes. In these bouncing models, each Big Bang is preceded by a big crunch, a universe collapsing under its own gravity until temperatures and densities become so extreme that space-time rebounds in a new explosion of creation. Traces of the previous universe might even linger in the form of imprinted gravitational waves or subtle patterns in the cosmic microwave background, cosmic hieroglyphs waiting to be deciphered. Then there's the quantum foam hypothesis, a seething, chaotic realm where space-time itself bubbles and churns like a boiling ocean. In this view, the Big Bang wasn't triggered by a collapse but emerged spontaneously from the froth of fluctuating energy. Picture a bubble forming in a pot of water. Our universe could be one of countless others, each born from random fluctuations in an eternal quantum substrate. Some versions of string theory take this further, proposing that our universe is a three-dimensional brain floating in a higher dimensional space, occasionally colliding with others. These collisions could unleash cataclysmic energy, resetting the cosmic clock in a cycle of destruction and rebirth. But the most mind-bending possibility is that time itself didn't exist before the Big Bang. What we perceive as before might be as meaningless as asking what's north of the North Pole. In this framework, the Big Bang didn't emerge from anything. It defined the very arrow of time, creating past and future in its wake. Yet even here, the universe teases us with clues. Anomalies in the cosmic microwave background, like the infamous axis of evil, could be scars from a pre-Big Bang phase, wrinkles in space-time that survived the transition. Others hunt for remnants of hypothetical cosmic strings, defects in space-time that might have formed in the unimaginable energies of the universe's birth. The deeper we dig, the stranger the questions become. Was our universe forged in the collision of higher dimensional membranes? Did it tunnel into existence from a quantum vacuum? Or is it just one note in an infinite symphony of parallel realities, each with its own laws and history? The cosmic veil doesn't just hide answers, it forces us to rethink what a question even means. Until we pierce that darkness, the universe's greatest secret might not be how it began, but whether beginning is the right word at all. Quantum immortality is one of the most unsettling ideas to emerge from the multiverse, a thought experiment where your consciousness might never experience true death, not because you live forever, but because it always finds a reality where you survive. Picture flipping a coin 1,000,000 times. In the vast majority of universes, the results average out to roughly half heads, half tails. But in a handful of bizarre branches, the coin lands on heads every single time. Now replace the coin with life or death choices, and you start to grasp the chilling premise. No matter how unlikely, there's always a version of events where you narrowly escape death, and your awareness follows that path like a train switching tracks at the last second. This isn't just philosophical musing, it's a direct consequence of the many worlds' interpretation of quantum mechanics. Every time a particle could decay or not, every time a neuron fires one way or another, reality splits. Most of these branches are mundane. A version of you picks tea instead of coffee, takes a different route to work, but some are existential. A bullet narrowly misses instead of hits. A fatal diagnosis turns out to be a lab error. In those vanishingly rare realities where every quantum dice roll goes your way, your consciousness persists, while countless other versions of you cease to exist, at least from your perspective. Critics argue this is less science and more solipsism, a trick of probability masquerading as immortality. After all, from the outside, you'd still die in the overwhelming majority of timelines. Loved ones would mourn, autopsies would be performed, and the universe would move on. Only from the subjective viewpoint of the winning version would it seem like survival was inevitable. Some physicists dismiss the idea entirely, pointing out that consciousness isn't a quantum process that can hop between realities. It's an emergent property of the brain, bound to one physical timeline. Yet the thought experiment lingers because it forces us to confront the nature of existence itself. If reality truly branches endlessly, what does it mean to be you? Are you the sum of all possible versions, or just the thread you happen to be experiencing now? And if consciousness can, in principle, thread the needle of survival forever, does that mean somewhere in the multiverse, there's a version of you reading these words 1,000 years from now, having cheated death through sheer statistical luck? The implications spiral into the surreal. Quantum immortality doesn't promise a pleasant forever, just an unbroken chain of near misses. You might find yourself the lone survivor of an apocalyptic event, or the only patient to outlive an incurable plague. In some branches, you could even become a Boltzmann brain, a consciousness flickering into existence with false memories of a full life, mistaking randomness for continuity. The universe, it seems, doesn't guarantee happiness or meaning, only the raw mathematics of persistence. Perhaps the most haunting question isn't whether quantum immortality is real, but what it would say about reality if it were. Would the multiverse be a merciful architect, ensuring no conscious experience truly ends, or a cold machine, indifferent to the suffering of its infinite variations? The answer, if there is one, lies beyond the veil where every possibility plays out, and every death is just a shadow cast by another version of you still alive. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace, as if reality itself were no more substantial than mist. Born in the hearts of stars, the fury of supernova, and even the echoes of the Big Bang, these nearly massless particles barely interact with matter at all. A block of lead a light-year thick wouldn't stop them, yet their very elusiveness makes them cosmic spies, carrying secrets from places light can't reach. When scientists first detected neutrinos streaming from the Sun in the 1960s, they uncovered a puzzle. Only a third of the predicted number arrived. Where were the rest? The answer reshaped physics. Neutrinos, it turns out, aren't just one flavor but three, and they morph between these identities as they travel, like a chameleon cycling through colors mid-stride. This phenomenon, called neutrino oscillation, was the first crack in the Standard Model's foundation. It proved these particles have mass, however infinitesimal, a revelation so groundbreaking it earned the 2015 Nobel Prize. But the deeper mystery is why they oscillate. Some theorists suspect undiscovered sterile neutrinos, a fourth flavor that interacts only via gravity, could be pulling the strings. Others wonder if neutrinos are key to the universe's matter-antimatter imbalance, why we exist at all. After the Big Bang, equal amounts of matter and antimatter should have annihilated each other, leaving nothing but radiation. Yet here we are. Neutrinos, with their subtle asymmetries, might hold the ledger of that cosmic accounting error. Detecting these phantoms requires feats of engineering bordering on madness. Take Japan's Super Kamiokande, a tank buried deep underground, filled with 50,000 tons of ultra-pure water, lined with sensors waiting for the rare neutrino collision that produces a flash of blue light. Or Ice Cube in Antarctica, which transforms a cubic kilometer of glacial ice into a particle detector by tracking the faint trails of muons created when neutrinos interact. These experiments have glimpsed neutrinos from supernova, black hole jets, and even distant active galaxies billions of light-years away. Each detection is like intercepting a coded telegram from the universe's most hidden realms. Yet the most tantalizing neutrinos are those that shouldn't exist. In 2018, Ice Cube spotted one with energy so extreme it dwarfed anything the Large Hadron Collider could produce. Dubbed the Ice Cube 170,922A event, this single particle packed the punch of a major league fastball, all condensed into a whisper of matter. Its origin unknown. Some speculate it was forged in a blazar's relativistic jet or a collapsing star's hidden firestorm. Others whisper it could be evidence of dark matter decay or exotic physics beyond our models. Neutrinos refuse to fit neatly into our understanding. They're too light, too slippery, too willing to defy expectations, but that's what makes them irresistible. Every unanswered question, their exact masses, their role in cosmic evolution, whether they're tied to hidden dimensions, is a thread tugging at the fabric of reality. They remind us that the universe's quietest voices often carry its loudest truths, and somewhere out there, streaming through rock, steel, and bone, a trillion more secrets are waiting to be caught. Galactic cannibalism sounds like something out of a cosmic horror story, but it's actually the universe's way of recycling, a slow, graceful destruction that births something entirely new. Right now, the Milky Way and Andromeda are locked in a gravitational tango, inching closer at nearly 250,000 miles per hour. In about 4 billion years, these two titans will meet, not with a cataclysmic explosion, but with an elegant, drawn-out merger that reshapes them into a single, colossal galaxy. And this isn't some rare cosmic event, it's the fate of nearly every galaxy in the universe. What's fascinating is how gentle these collisions really are. Despite the dramatic name, stars almost never physically crash into each other. The distances between them are so vast that even when galaxies overlap, their stars slide past one another like ships in the night. But gravity, the universe's ultimate sculptor, doesn't need direct hits to work its magic. As the galaxies intertwine, tidal forces stretch and warp their shapes, flinging stars into long, streaming tails that resemble celestial brushstrokes. Over billions of years, their spiral arms unravel, their cores merge, and what was once two distinct galaxies becomes something new. An elliptical galaxy, a smooth, featureless orb of stars with no trace of its violent past. We've seen this play out across the cosmos. The antennae galaxies, a pair locked in a fiery embrace, are a preview of our own future, with vast arcs of gas and dust lit up by newborn stars. Then there's NGC 7752, nicknamed the Atoms for Peace galaxy, where two spirals have nearly finished merging into a single glowing ring. Even our own Milky Way bears the scars of past meals. Dwarf galaxies like Sagittarius have been torn apart and absorbed, their stars now strewn through our halo like cosmic crumbs. But mergers aren't just about destruction, they're also engines of creation. When galaxies collide, their gas clouds slam together, triggering bursts of star formation so intense they outshine entire galaxies. These starbursts are fleeting, though. Eventually, the gas runs dry and the new galaxy settles into a quiet middle age, its spiral structure erased forever. That's the bittersweet truth of galactic cannibalism. To build something new, the old must be torn apart. And here's the twist: we're not just bystanders in this process. The Milky Way Andromeda merger will fling our solar system to the outer edges of the new galaxy, a cosmic relocation that might just spare us from the worst of the chaos. But by then, the sun will have long since swollen into a red giant, rendering Earth uninhabitable. The universe doesn't care about individual stars or planets. It's playing a much longer game, one where galaxies are the pieces and gravity is the rule. What's mesmerizing is how these collisions reveal the universe's relentless creativity. Every time galaxies merge, they rewrite their own histories, blending stars from different origins into something unrecognizable. It's a reminder that even in the vast, cold expanse of space, nothing stays the same, not even the galaxies themselves. Exoplanets shatter our old assumptions about what a solar system should look like. Just decades ago, we knew of only 9 planets all orbiting our sun. Now, telescopes like Kepler and TESS have revealed over 5,000 alien worlds, each rewriting the rules of planetary science. Take HD 18973b, a scorching gas giant where winds scream at 5,000 miles per hour, hurling molten glass rain sideways. Or GJ 1214b, a water world so thoroughly drenched that its entire surface might be a single planet-wide ocean deeper than Earth's Mariana Trench. These aren't just curiosities, they're proof that nature's imagination dwarfs our own. The real thrill lies in the Goldilocks zone, the orbital sweet spot where liquid water could pool on a planet's surface. Kepler 452b, often called Earth's cousin, orbits a sun-like star in this region, with a year only 20 days longer than ours. Then there's TRAPPIST-1, 7 rocky planets, 3 of which bask in their tiny star's temperate glow. But habitability isn't just about distance. Tidally locked planets with one side permanently facing their star might harbor life in the twilight strip between eternal day and endless night. Others, like those orbiting red dwarfs, endure violent flares that could strip atmospheres unless, like Earth, they're shielded by magnetic fields. The hunt for biosignatures, chemical fingerprints of life, has turned atmospheres into cosmic crime scenes. When the James Webb Space Telescope analyzed the air of K218b, It spotted methane and carbon dioxide, gases that on Earth often hint at biological activity. But false alarms abound. Phosphine gas in Venus's cloud sparked speculation, only for follow-up studies to question its origins. The line between geology and biology blurs when volcanoes can mimic life's chemistry, or when subterranean oceans like those on Europa or Enceladus brew complex molecules without sunlight. Could intelligence exist out there? SETI scans for radio signals, but an advanced civilization might use lasers, neutrinos, or something we haven't imagined. The WOW signal, a 72-second burst detected in 1977, remains tantalizing but unconfirmed. Meanwhile, Tabby's star, with its erratic dimming, once fueled speculation about alien megastructures until dust clouds proved the likelier culprit. The universe seems to tease us, dangling possibilities just beyond reach. Every new exoplanet is a mirror, reflecting not just starlight but our own place in the cosmos. Are we alone, unique, or just one thread in a vast tapestry of life? With missions like the upcoming Habitable Worlds Observatory, the veil keeps lifting, one world at a time. Our journey beyond the cosmic veil has peeled back layers of reality to reveal a universe that defies every expectation, where black holes rewrite the rules of time, dark energy stretches the fabric of space, and entire dimensions might lurk just beyond our perception. These aren't just abstract ideas scribbled on a theorist's chalkboard. They're the universe's way of whispering that we've only just begun to understand the stage on which we stand. Think of it like stumbling into a darkened theater mid-performance. We've caught glimpses of the set, heard fragments of dialogue, but the full story remains tantalizingly out of view. What makes these mysteries so exhilarating isn't just their strangeness, it's how they humble us. For all our telescopes and supercomputers, we still can't explain what 95% of the cosmos is made of. Dark matter eludes our detectors, dark energy mocks our equations, and quantum particles flirt with the impossible right under our noses. Yet this isn't a failure, it's an invitation. Every unanswered question is a door waiting to be kicked open. When Einstein first imagined riding a beam of light, or Hawking dared to theorize about black hole radiation, they weren't just solving puzzles, they were reshaping what we thought was possible. The beauty of cosmic exploration lies in its democracy. You don't need a PhD to spot the anomalies in telescope data or to wonder why quasars pulse like cosmic metronomes. Some of history's greatest breakthroughs started with someone staring at the night sky and asking, "Wait, that doesn't make sense." The next leap could come from a lab, a laptop, or even a backyard telescope. That's the thrill of living in this golden age of discovery, where tools like the James Webb Space Telescope and gravitational wave detectors are handing us keys to doors we didn't even know existed. So where do we go from here? The cosmic veil isn't a wall, it's a horizon receding as we advance. Maybe the answers lie in neutrinos ghosting through our detectors, in the quantum fuzz at the edge of a black hole, or in some yet undreamed experiment that'll turn physics upside down. Whatever the path, one thing's certain: the universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's what makes the search so exhilarating. As we wrap up this voyage, remember you're part of the story. Every time you look up, every time you question, you're adding to the collective curiosity that drives us forward. So keep wondering, keep exploring, and who knows, the next cosmic revelation might have your name on it. And hey, if these mysteries sparked your imagination, let us know in the comments which cosmic enigma keeps you up at night. Don't forget to hit like, subscribe, and join us as we keep peeling back the universe's layers, one mystery at a time. The cosmos is waiting, and the best discoveries are still ahead.